walk us through how to build a decentralized currency. The subtitle is Merkleized Transaction Histories, Byzantine Fault Tolerance, and Decentralized Networking. Oh my. If that scares you, hopefully by the end of this talk it will not. So the agenda here, I'll give a sort of brief intro of this thing called cryptoeconomics that I'm really into. And then we'll kind of walk through the sort of building blocks of a decentralized currency. And there'll be some code samples in Clojure, and I'll show you kind of how all that fits together. All that will kind of be going between the slides here and then like a REPL that I've set up. So we'll get a taste of this like interactive programming that we should all love. And then perhaps I'll wrap up with why Clojure is great in general for this and really everything. So who am I? My name is Alex Stokes. I like to call myself a cryptoeconomist. I've been studying it since like 2011, so many years now. You can find me at @AlexStokes. That's my email, GitHub, all the stuff. I have a website at stokes.io. By the way, can everyone see the TV okay?
Yep.
It's a little small, but okay. Hopefully we'll be okay. So first, what is cryptoeconomics? Here's a little dictionary definition. It's the study of the allocation of scarce resources under adversarial conditions. And an example here would be like, well, perhaps I should take a step back and say, okay, how does this kind of fit into what we already have? Well, we already have cryptography, and there the point is to communicate under adversarial conditions. And an example there is like, I want to send you maybe like a secret letter, but I want to send it on the internet, which is every computer in the world connected together. So if I don't do something special to it, anyone can kind of intercept that message and see what I'm trying to send you. So I can't really send you the secret. The sort of catchphrase I have for this is proofs and promises, which now I'll explain what that is. Basically, cryptoeconomics is this thing where we can sort of make strong statements about the past, and these are the proofs, right? So we use tools from cryptography to say, okay, this thing happened at this point in time, and I can tell that because I can put this data into this algorithm, and if basically, sort of fundamental physical laws about the universe don't hold, then like this thing's broken, but I kind of think that the universe usually does hold, so we're good to go. Examples there would be like hash functions, digital signatures, Merkle trees, which are really cool. Basically everything should be Merkleized. Zero knowledge proofs, which are even cooler than Merkle trees. Asymmetric encryption. Basically all of this takes somewhat sophisticated math and like lets you do magic. So it's pretty cool in that way. Then the other half would be those promises. And these are statements about the future, right? So it's like, okay, an example would be like an IOU. If I want to loan you $5 today, I can basically get back an IOU from you that says, okay, I'll pay you back $5 plus some interest in the future. Examples we kind of see in crypto would be rewards, like monetary rewards, also punishments. Sort of these algorithmic ideas around interest rates, issuance of some currency, inflation or deflation rates, this idea of like marginal cost versus expected profitability. So if you're familiar with mining, which we'll get into in a little bit, you'll see this sort of trade-off that a miner has to make between, okay, do I like sort of commit my hardware to doing this puzzle, or should I not, because like it's just not going to make sense for me in terms of profits or revenue, obviously. So we have this fun little picture I drew where this is supposed to be like a time cone, like space-time, if anyone's familiar with physics, but basically you can sort of sit here in the present at this dot, and you can look back in time, and you have proofs to like sort of do cool things there, and then you have this idea of promises that you can then apply towards the future. So the point I want to make here is just that we have this really powerful toolkit to do really awesome things. We haven't really had these tools in this exact combination before, and it's like actually pretty revolutionary, which hopefully that's why you're all here, to learn more about how that's so. So, a decentralized currency. A blockchain is just a Byzantine fault-tolerant distributed consensus protocol that emulates a shared ledger using asymmetric cryptography despite a central coordinating authority. What's the problem? If anyone knows the monad joke, that's the monad joke, but for crypto. So I had these words here that I kind of picked out, and let's just kind of dig into the important ones. So there's when we want one of these like cryptocurrencies, what are we looking for? We're looking for something that's decentralized. what that means here is that sort of there's no central person or identity, or we'll use the word actor that has like the entire state or like sort of the truth, right? So like for instance, if you like want to know the meaning of a word, you could like go to a dictionary and look it up. But then like who put the dictionary together? Well, we can find out, but I might not trust them to like have assembled a dictionary. And so you can imagine a decentralized dictionary where in some sense, everyone has a copy of the dictionary, and so I don't have to like trust you or a friend or someone you know to tell me the meaning of the word. Another property here is like Byzantine fault tolerant. This is a very fancy phrase with like a lot of academic literature behind it that basically says if you have strangers on the internet and they have incentive to cheat or lie to you, they will. So it's yeah, that's something we need to come across, because again, the setting here is you have essentially strangers on the internet all trying to come together to do like one cool thing. And yeah, some of them, realize that they could have some like short-term windfall by like lying to you about, let's say, the price of Ethereum or something like that. And then finally, in this setting, we want to come together and like have this shared ledger. So we have this abstraction of like who owns what, for some abstract sense of who and what. And the game here is to agree on the state that we can all come to, and like how do we do that when again there's no central person we can like go and check about the state of things. So let's build a currency. So let's start by kind of defining what a currency is. Well, basic definition is sort of an abstraction of exchange. If I went to trade, let's say a cup of coffee for like your shoes or something, then instead of me having the coffee and you having the shoes at the same moment in time and space, we could actually just sort of trade this abstraction. We'll call them coins, currencies. We all have these like sort of everyday notions of currency, but it helps to kind of be precise about what we're talking about, or at least to think about it. So you see these pictures here, and basically the idea is, it's not that we have physical coins here in our cryptocurrency. We just have like zeros and ones. So we have bytes floating around, and again the task will be taking these bytes and basically building a currency so that we have something that mirrors our typical intuitions around these things. So it's it looks less like the zeros and ones and more like the gold coins. So we have coins. And it turns out in currencies, coins also have owners. So, we usually think of individual actors who are like holding the coins, and they can trade the coins, they can bury the coins, do whatever, right? So coins have owners, and we'll also say that basically owners can then swap currency sort of atomically in something called a transaction. And here's a little photo of that, kind of what I just said, where the person on the left wants to spend 5 coins, the person on the right. In return, they get 2 coins back and then also some coffee, right? So like I bought some coffee from you and you gave me change. So there's a bit of an issue though when we move to the decentralized context, because basically you need to know the state of this ledger, let's say, right? You need to know like how many coins I have before you can kind of accept that I have the coins I claim I do. And the way we usually get around that, again, looking at this photo, we have, let's say Alice wants to send 5 coins to Bob. And because we're kind of in this digital context, Alice could kind of very easily fabricate maybe naive implementations we could think of for these currencies. And so, for instance, if you look at traditional things like Visa, so like Alice gives Bob a credit card number. And then if I just get a credit card number, how am I supposed to know like what your credit is, right? Like what your balance is. And so if you're Bob, you usually would go to Visa. The problem though is that Visa is a centralized authority that we don't really want to sort of be governing these interactions, so there's nothing like this. So like what do we do? So yeah, we'll decentralize it. So we get around having to go to any particular single authority by basically making everyone their own authority. So everyone has a copy of the ledger that they maintain. The trick now is that we all have to agree on the order of the transactions and like the histories that go into that. Basically, we're going to take all the transactions that have ever happened for all time and put them in the same way into an append-only log. And the trick there is that we have to do it in the same way for all time. If we basically can kind of think of it as like reduction or fold, like we might see in Clojure, where like if you start with the sort of same state and apply the same data in the same way, you end up with the same result at the end. So that's what we ultimately want to do, but as I've laid out, it's actually not clear how to do that at all. So here's a little Clojure code. Can everyone see that okay? It's dark on dark, but either way. So we have some Clojure code here, essentially pseudocode to sketch out what we're trying to do. Let's say we want to get a balance for someone with this identifier that's Alice, and we're basically going to hand off the transaction stream of all possible transactions. So in some way we get the transaction stream. We say, okay, to get the balance for Alice, let's say it's really straightforward. We just get all the transactions in the same order as everyone else, and we basically reduce that against the current ledger with this apply transaction to ledger function. The trick though here is where it says that a miracle needs to occur because we basically have to pick the same order as everyone else. And moreover, the orders that we pick have to not do things that we wouldn't expect of a currency. For instance, duplicating coins, creating more coins than you didn't have before, these types of things. So like I kind of started sketching, there's some challenges here. The first one is if everyone has their own ledger, how do I actually know what the real ledger is? How can I make sure that only I can spend my coins and not you can spend my coins? Because you could imagine if I have the ledger for you and I just be oh yeah, let me change this 200 to a 20 and then move the coins over here to myself. Well, I just stole all your coins. So we need some notion of ownership and some way to build that into the protocol. And then moreover, we have this somewhat bigger issue, which is okay, if anybody can in turn propose a transaction history on this decentralized network, how do we pick the right one? How do we pick the right history out of all possible histories? Where we have to constrain the histories a bit to sort of have valid histories that make sense in the first place, but then over there, or even within that subset, you can still have histories that do nefarious things like double spins, like I mentioned, or delete coins, or all sorts of things. So basically, we need some mechanism to figure out, okay, given all the data I've seen, which again might be a partial view of the sort of total network state, how do I figure out the right thing? So like I said, we need to build some ownership mechanism. We're going to do this basically using cryptography. So your notion of yourself on this thing will be essentially a cryptographic key pair. And we'll use some asymmetric cryptography to basically say, okay, you can make statements about ownership by essentially signing these statements. Which, by the way, should I go into asymmetric cryptography? I probably should mention it. So basically, the idea is you basically have two big numbers, and one of them is private and one of them is public. And again, through some really cool math, it turns out that you can do things like make a signature that's unique to you and unique to the message and the thing you're signing, and it doesn't reveal your private key, but anyone with your public key can then verify that it was you who signed it. And so signatures is one example. There's also encryption. So I could take a message, I could encrypt it with my private key. It would look like random gibberish. I could put it out on the internet, and then anyone with my public key, let's see, yeah. So you would encrypt with my public key, and then I could decrypt with my private key. Basically, cool stuff. And I'll go into a little more detail how it applies in blockchains. And then the second thing is, in order to figure out this, how do we figure out what's the right sort of stream of transactions that we're looking for? We're going to basically take some ideas from economics, and then also some of the classical consensus algorithms for doing so. So the bottom line is we're going to sort of fuse these two things together. We're going to get a decentralized ledger that maps addresses to coins. So the first bit is who owns which coins, this notion of ownership. So again, like I kind of mentioned, there's this public key, private key cryptography notion, which maybe will make more sense if it didn't once we get to some of the code. And then basically to spend a coin, so let me take a step back. So for every key pair, we're going to have this public key and private key. For every public key, there's basically an algorithm to get an address. And these addresses are basically going to be able to spend coins. So they're basically going to map into balances on the ledger. And then in order to spend the coins, you basically have to provide a proof to the entire network that you can do so, and that's where this digital signatures come into play. So here's the demo. And I might have to, here's one of the demos. I'm going to jump into some Clojure code. Can everyone read the screen okay? Okay. So basically, just to kind of go through every line, there's quite a few namespaces here, and we're basically just importing most of them. probably all of them. I'm using this component sort of framework, component library from Stuart Sierra. Maybe some of you have heard of it. It's a really great way to basically organize your application as like a system. It's really easy to tear up and tear down. It's great. It's really great for like interactive development of the whole thing. But enough of that. So now we're going to look at keys. So the first thing we can do is make a new key pair. I'll do this, possibly. Okay. Let's see. So basically, what I did here was evaluate this form at my REPL, and it basically pretty printed over here. So for instance, we have some properties in this key pair. So really important would be the private key and the public key here. And we see here it generated this address. So we'll see in a minute how to basically get those. There's some functions here to basically derive those given a key pair. So for some keys, here's a serialization of the public key. Then this would be the private key, and then here's the address that we get from basically hashing the public key, and we can go look at that in a second. So let's do that. So it's pretty straightforward. This is kind of the algorithm right here. You basically take a public key that's been encoded in some well-known way that some cryptographic standard has come up with. You take those bytes, you basically hash the bytes. I'll explain what a hash function is. So a hash function is, again, some more cool math. Basically, you feed it an arbitrary number of bytes, and then it will return you a fixed number of bytes back with hopefully the guarantee that the bytes you get back are completely unique for every possible input. Which is great because it gives us sort of fingerprints of things. But either way, so to make addresses here, we basically take the bytes, we hash them, take 20 of them, and then base 58 encode. That basically just means make it a little more human readable so we don't have to just stare at zeros and ones.
Why 58?
It's what Bitcoin uses. They might have some rationale. I'm not aware of what it is.
I think it removes the characters that look similar. Zeros and O's.
There is part of that, yeah.
I have a question. What happens if there is a conflict?
Conflict where?
Yeah, okay, the collision.
A hash collision.
Take the first 20. Yeah.
Terrible things happen.
Okay.
Yeah. Well. Yeah. So you're a little safer because if you have a collision in the first bit, like basically once you've hashed and then there's you just win it, right? So you'd have to have a hash collision in order to have the sort of prefixes be the same, right?
So is taking 20 just like good enough for practical purposes?
Exactly, yeah. It's just like I'm a human. I don't want to like read 40 bytes off of something, so like I'll just take 20 because that's still like some huge number. So it's good enough. It's kind of like how with IPv4 we're like, oh, we'll never need more than this many addresses. It'll be great. Cool, yeah. And by the way, feel free to ask any questions whenever that might actually be more helpful for everyone if this is more interactive rather than me just walking through code. But yeah, so hopefully that kind of makes sense to everyone. Without sort of digging more into cryptography, there's like a bunch of cool math we can do to basically say you have a secret that lets you be sort of an independent identity on this blockchain, and you can basically use it to kind of control your coins. So we're back here. Okay, so now that we can control coins, we're going to talk about sort of the transaction format. And by the way, so a lot of the implementation, so yeah, this Clojure here is representing this, at this point, basically a pretty complete blockchain. It's basically following a lot of the design of Bitcoin, so it's a proof of work blockchain, which I'll explain in a minute. Sort of the same transaction format and different things like this. So part of that model is what we call UTXOs. So a UTXO is an abbreviation for unspent transaction output. And the idea is that sort of having this like sort of mutable state idea, where it's like you have an account that like sort of sits there and has your balance, and you can like get and set the balance through like different actions. You now basically have to append a transaction to like change anything about the state, about the ledger. So hopefully that kind of makes sense to some of us in the Clojure land, where like we very much understand the importance of doing that, or at least some of the nice properties you can bias by doing that, rather than just like poking at a bunch of mutable state. This photo in particular, I actually think is pretty confusing. It came out of the Bitcoin white paper, but I just put it here kind of for completeness' sake. I'm going to walk you through what I think is a little more, what's a little more clear sort of description of UTXOs. But basically the idea is that in order to, the high level idea is that in order to spend coins, you basically have to present a proof that you have, well, let me take a step back. What makes more sense is to say, in order for me to like have coins on the network, it's required that I give a puzzle you have to solve in order to spend them, which I realize is a little backwards, but hopefully this will make sense if I explain it a little bit more this way. So I have this little photo over here, and let's say there's this entry in the ledger. This is one of our UTXOs. It basically says that someone named Alice has said that someone named Bob can spend 10 coins. And that's kind of the thing. So in order for that to happen, though, Bob basically has to prove that he is Bob. The way that we'll do this is we'll use digital signatures, which again is this unforgeable sort of impersonal record of like who different people are.
Why is Alice involved? Does this constitute a transaction from her to him?
This would be, so for a given transaction, there are multiple inputs and multiple outputs. So the transactions are the mappings basically between these UTXOs to make new UTXOs.
So what does Alice have to do with what Bob can spend?
So Alice wanted to give, so this says that in the past, Alice has given someone named Bob 10 coins. Because now if Bob is Bob, Bob has the private key, and so he can very easily then produce a signature that proves that to everyone, and everyone can update the state of their ledger.
So why is it phrased in this peculiar way?
I don't follow.
Yeah, maybe I can. So somebody births a coin. When you spend that, take that as written, that there's some process.
We'll get into later. Yeah, we'll figure out later how coins are made.
When I spend that coin, I'm now saying that I have the authority to tell the rest of the universe that you now have the authority to spend that coin. You give that to somebody else. There's another transaction. So it's this chain of spending. It's as if that penny or that dollar in your pocket could tell a story as to how many wallets it's been in. And so these chains of UTXOs, which actually become a branch along a Merkle tree, is by which you know that that coin is at the end.
So she's the prior.
Right, she's the prior.
Exactly, yeah. So that's what this is supposed to, this is this chain that he's talking about, where it's like, basically there are some inputs that come off the page that goes into this first transaction you see on the left. And essentially what this is saying is that you have to present owner one's signature in order to move the coins to another place.
Okay. Or something like that.
All chain is persistent. Trace it back home.
Right. So yeah. So maybe if I keep walking through this, will make sense. This is like one of the stumbling blocks of at least Bitcoin because it's a little bit backwards.
So doesn't
or at least it's just not
it
familiar.
grow without limit, the chain?
Well, yeah. Well, that's yes, it does. But there have been many wars fought over that exact question.
That's okay.
But yeah. So basically, you could keep it pending for all time.
Don't think too far ahead. Don't think too far ahead.
Sure you make money.
Don't think too far ahead. Have another beer.
Okay, so here's this magical step, right? So Bob has decided he wants to then take these 10 coins he has a claim to and give them to Charlie, right? So the way that he does that is he makes this transaction, which is this next frame. He attaches his signature saying like, yes, this is the UTXO I'm trying to spend. And now whoever is Charlie, if they can provide a signature, then everyone has to agree that Charlie now owns the 10 coins. But that's going to happen in the future, right? So this is still just sort of adding another UTXO, another output. And yeah, this is just the full picture together. So the idea, and yeah, I guess keep asking questions totally if that didn't quite make sense. But the idea is basically you keep appending these, you append like a chain of signatures for each sort of unique coin, and that's how you track ownership. Here's another thing. I think this is from the bitcoin.org site, just kind of showing, in general, we have this graph of transactions where like you have many inputs, many outputs, and they can go to different places. And one way to think about it is, again, you start like the genesis block, you like reduce this whole graph, and then you end up with a ledger, which I will show you now. Okay, let's see. So the first thing is we have this nice little function that makes a transaction. Basically, there's like a couple things we have to do. This transaction in particular just takes, it takes some number of outputs. It basically spends some value that we'll provide in a second, and it basically sends everything else, in the case that there is more than value inputs, back to the spender. So we'll start here by defining some keys, and these are these cryptographic keys I just mentioned. So, you know, we have some key pairs. That's not helpful. Let's see. If only Emacs would stay zoomed. So anyways, here's some keys. Again, basically, there's just large numbers that let you do these magical things. There's basically a sender and a receiver. In this case, we're going to send 10 coins as our value. We're going to pick out the ledger from the system, I hope. Maybe we're not. Let's see. Unbound. That's terrible. Well, now we'll get a little flavor for interactive debugging with Clojure. So the cool bit is, so I evaluated this expression and got a null pointer exception, so something is off, and it shouldn't be. But basically, the cool thing is I can kind of check this form by form. Okay, maybe this is the problem. Yeah, that's the problem. Still a problem. Bear with me 1 second. Okay. Anyway, it seemed to have dropped the reference. Maybe I said something up wrong. Anyways, okay, here we go. This is what I want to show you. This is the ledger. It's basically organized by these UTXOs, which are identified by a transaction hash and then an index into that particular transaction. You have a question? Bigger. So it'll be a little hard to see because these hashes get large, but basically the idea here is like, this is referencing, so this data here, this hash and this index, that's referencing one of these outputs here. So like, pick an output. But basically, these forward arrows are like what kind of dangle in terms of being free to like then use later. So you see here, there's these unspent outputs. And then what you get back, or at least what's attached in this map, is the full output here, which has something like its value, the script, which we'll get into in a second, and then again, just the same hash and index information. So that's great. And now we're going to make a transaction. Possibly. Oh, that's weird. Okay, sorry this isn't buttery smooth. Why did, oh.
We know it's a real deal.
Yeah, I know what I did. Okay, so yeah, basically it's just to show, again, how to build a transaction. So, is that big enough? Again, just a map. Again, one of the sort of benefits of Clojure is that there's this emphasis on data. I kind of like to describe Clojure as like a great DSL for like manipulating data, which is like very abstract, but if that means anything to you, it's awesome that it's so good at being that thing. So we have some inputs, which again are references to previous outputs. We then have new outputs that describe how we basically want to take the incoming value and split it up. So like as an example here, we basically had this output, an input value of 128. So basically, someone gave someone else 128 coins, and then this person decided to spend them in the following way, by basically spending 10 coins to this address here. And then the remainder coins, they basically send back to themselves. So these addresses should match. And they do. So that's great.
Why do they send them to themselves?
It's like change. So again, there's this notion of like an atomic transaction, and that you can't basically, once you consume one of these outputs. So like once you basically picked one of these arrows, one of these outputs, you can't ever pick it again. So if this is for like 100 coins, and
You gotta take the whole 100.
you have to do something with it. If you only spend 50, then you basically burn or you like delete the other 50. Like no one can ever get it ever. It's just gone.
So if you send them to yourself, that fills out the.
Well, yeah, if you want to keep them, it's just like change, right? So it's like if I gave you $20 for like a $10. I keep going back to coffee. Let's say I give you $10 for a $5 coffee, then like I should get $5 back, right?
Copies are getting more.
Yeah. Well, that's a different talk. So great, we have this transaction, and this bit that I kind of was poking at but didn't explain the script. So I'm not sure I'm gonna have time to like kind of go into this in depth in terms of why it's a script and all of that, but the takeaway here is that Bitcoin has something called script. It's actually a language like Forth. Forth is a stack-based or like a concatenative language where you basically just like push a bunch of opcodes together and then they do things against a stack. And the idea is that with Bitcoin, you actually have this like somewhat general notion of being able to like do more complicated things than just say move coins from me to you or move coins from here to there. And so yeah, basically I've implemented one type of transaction, pay to public key hash, which is basically paying to someone's address. So that's why this is called script and all of that. So as part of that though is for every transaction, you basically run a little bit of code. There's essentially a VM. The way that you make a transaction is like you serialize to some opcodes, and as part of validating a transaction, you actually have to make sure that the inputs and the data basically verifies against the code. And so that's how you encode these constraints, like you need to be able to solve this puzzle to spin these outputs. The puzzle is you need to provide a signature that claims or that proves that you actually can spin the coins that you claim that you want to spend. So again, that's why we see here, here's that data. There's a public key. The reason you have the public key is because you can then verify that against the address with the algorithm I showed earlier. There's a signature here, which again, this proves that you're actually the person you claim you are and that you actually can move these coins. So this kind of pokes at that and just looks at different pieces of it. The important bit here is this valid pay to public key hash function I have, which basically just describes what I said. It takes the input data that it expects for this particular type of transaction. It makes sure that everything lines up cryptographically and sort of a correct node. So if you're running the software to like sort of say participate in the network, you should only accept transactions that basically pass this check, because otherwise it's someone's just trying to steal someone's coins or like something even crazier. So you just wouldn't want to do that. And basically, yeah. Oh well, we can look at the proofs. Although we kind of did, but basically, let's see. It's kind of exactly what I said. You have a public key. The hash is useful. You need the hash actually to verify the signature and the signature. So either way, like you saw, we get back true because everything's good to go, and that's great. So now, kind of like I've said a couple times, you can imagine having a starting state, then you have a bunch of transactions, you have a starting ledger, and then you can do some fold to apply everything. So here we're just going to walk through a single step of that reduction, this apply transaction to ledger. And that gives us a lot of stuff. So basically it takes an input ledger, and then we get back this ledger. And I realize this might be a little tricky to parse. But basically, let's look at the ledger. Is this the right ledger? And let's see what we're trying to do here. So looking for, okay, so what we're doing is we're going to take this here, this output. I know that because basically we can dig in here, but the data ends up in this proof that it's identified by a hash. And this hash here is 60E. Maybe I'll point it out. Basically, the one that we're trying to spend is this transaction that has this hash, which is this one. Oh, you can't see that. Anyway, it's up here. I promise. Can I edit this?
Split window wisely.
What?
Split the window wisely.
Well, I was just going to do this.
60.
Anyway, let's see. Yeah. Well, you shouldn't. You should verify everything I'm saying. I could be, trying to convince you guys to play with this blockchain, and it could just send me all the coins or something terrible, right? So we have this, and then what we're going to do is we're going to apply this transaction that basically spins this 128 value output, and then there should be 2 new outputs. So again, just to follow along, this is sort of the key to this output here, and we're going to spin this via this apply function. So now we'll look at that. And I'll do the same thing again. So, well, first we'll look and see, and there's no 60, so that's gone. And we should basically get back, here we go. So then we have this value of 10, which was the number of coins we were trying to send to someone. And then we have the change that we have, which is 118. And so hopefully this kind of makes this a little more concrete, that now if I'm the original sender, I now have these 118 coins like spin to someone else. And they're just, again, sort of in my wallet. Is a term we like to throw around. They're under my control. I can do what I want with them. Okay.
Question. Yeah. Why can't you just send 10? Are there like certain?
Well, you could, but then so you have to pick an output. Like basically, so every transaction has inputs and outputs, and inputs are just previous outputs. That's all they can be. So like if a previous output, so let's say, let's just say you have the ability to like spin an output that has like 100 coins. Then what if you don't want to spend 100? You could send 10, but then like I was saying a minute ago, what happens is that if you publish that transaction and then it gets included into the blockchain, what happens is that you only spend 10 of that output. That output can never again be used, and so you've lost the other 90. So you probably don't want to do that, unless you do. Yeah, let's jump back into this. So we've kind of, hopefully I've helped you understand a little bit of sort of this notion of ownership and how that's implemented. We have digital signatures and chains of them that basically trace the history of coins over time. But the problem is that we still don't have a global order. Basically, if we go back to like this photo here, right, there's like this graph, but you could imagine like many possible graphs, because again, anyone could kind of publish these graphs on the network. And sort of, as it stands, I wouldn't know which is the right one, because they could all be cryptographically valid, but they could still do things like double spins, where like I basically showed 2 different versions of this graph to 2 different people. And so in one case, let's say I have 100 coins, and I send you the 100 coins, and I get back like a Ferrari. While you're basically, coming to terms with that and processing it and like, sort of thinking about the transaction, I could then take sort of the duplicate graph to someone else, another Ferrari dealer, not tell them I spent the coins already, and then give them this picture, and then they would, without anything else, they wouldn't really know if it's valid or not. So they might just go along with it. Then I basically have spent my coins in multiple places. And we don't want to do this because like it's not a currency, right? Like I can't spend a single dollar 2 places simultaneously. So it's really important that we have this global order. The sort of name of the game here is like we need to have certain transactions that happened before other transactions. But again, if any of you are familiar with like some like distributed system stuff, basically there is no time. Like clocks are really hard, and times there just isn't. You just shouldn't rely on time. If you do, bad things are going to happen. So what are we going to do? And what we're going to do is kind of 2 things. The first thing is that we're going to take transactions. We're going to bundle them into blocks. You'll see I'm building into the blockchain. So you have transactions. They get bundled into blocks. And the way we do this is basically you say, okay, the protocol sort of mandates that the only way you can advance the state of the ledger is to apply a block to it. So a block is a group of transactions. And that's sort of like a point of condensation for all the transactions, right? You can think of like all possible sort of transaction orderings, and then you kind of have to serialize them into blocks, which is helpful because now you can start to make stronger statements about their ordering. Then we're going to go another step further. We're actually going to link the blocks. We're going to link the blocks by their hashes. So basically we're going to take the entire block data. We're going to, actually a block header, but that's a detail. Basically you take the block data, you run it through a hash function, you get back a unique hash for that block, And what we're going to do is then say, okay, for the next block, that block has to contain the hash of the previous block. So sort of like a reverse pointer. And the way that this works is that in order to have the hash of the thing, it has to exist. Like you're not just going to randomly guess the hash. So that implies that as long as the laws of physics hold, that like if this thing has the hash of this thing, then it has to be the case that this thing came first. And again, it gets rid of like many like possible orderings of transactions that we just wouldn't want to see in a currency.
You talk about what constitutes a block?
Yeah. So here's a block. Here's a little cartoon of blocks at least. A block is a bundle of transactions. Again, there's like a hash of a block, and again, they include a previous block's hash. So I don't know if you can read that well, but basically, here's a block that points somewhere else. Here's a block that has a previous hash of ABC, and that's the hash of this block. And this way we form, like a hash chain. You'll hear the word sometimes. So yeah, that's essentially the blockchain. And now we will dig into some of that in a little more detail. Let's see. How do I want to do this? So let me try this again. Okay. It didn't explode this time. Great. So we're going to pull out the blockchain and the genesis block. So the genesis block is just like the very first block in the chain. You'll hear it called that. So let's take a look at it. And again, because in order to like pull off our sort of, our reduction algorithm, what we need to do is we need to start with the same state. So the genesis block is actually really important that everyone starts with the same one. Usually this is just hard-coded into like different blockchain softwares, like the actual software you download has this hard-coded in. You can do things like go to Twitter to get like a block hash and like verify it that way. There's like different things people think about, but basically it's really important that you get this, because if you don't get this, you're just on a completely separate network from like everyone else. And yeah, so we see here, here's a block. So again, the hash, the all-important hash, blocks have hashes. There's a nonce that is pertains to mining, and I'll get to that a little bit later if we have time. There's a timestamp, which is great. There's a transaction root. So like someone mentioned, basically you don't actually put sort of the full sort of raw transaction set into the block. You actually just include, so you put into this thing called a Merkle tree. The Merkle tree basically is you can think of it as like a really fancy hash function to give you back this identifier, which again is just like a hash of hashes. If there's time at the end, I'll show you and I'll explain more what a Merkle tree is. But basically all you should take away from this is just that it's sort of a unique way to get this fingerprint for a set of transactions. There's a difficulty that's related to mining. We'll get to in a second. This is the genesis block, so there is no previous hash. All the other blocks will have previous hashes. And then we see the genesis transactions. So for instance, there's this one, so I can touch on this now. The way you make coins, which I kind of left out so far, the way that you make coins is that whoever gets to mine a block, so there's a process by which you get to mine. You basically are elected, sort of, well, not round robin, but you're elected to mine blocks in a certain way that we'll get to in a second. And it's kind of the reward for doing that is that you get to make a transaction that just gives you coins out of nowhere. So this is how coins are sort of minted or injected into the system. And it's basically to incentivize these people to form these blocks. So yeah, I poked through the transactions. Here's another block just to take a look at it. So again, we have this Coinbase output. The Coinbase just refers to basically the person who made the block. Here, like I said, we have the previous hash of the thing. So this wasn't the genesis block, but this was the one after that. So we have the previous hash there. Again, different transactions, different transaction routes. Then we have the hash of this block. So everything kind of checks out. And here's the full blockchain so far. So the way this is set up is there's basically a node of 3 peers, or I guess I should say a network of 3 peers running locally on my machine. They kind of have all agreed on this single blockchain, which again is just this vector of blocks, which yes, a lot of data. So let's take a look at a smaller amount of data, which is this chain of hashes. And basically it's just to say, okay, the first entry is a genesis block. There's no previous hash, but there's a block hash. Now this is the same hash pointing back to the genesis block, new hash. This is pointing to the previous block, and then a new hash. And then the idea is you would add another block at the end of here.
Question.
Yeah.
So a block represents some set of transactions.
Yep. So whoever gets to make the block can pick any transactions that they have seen, and they get to pick it. Well, it's not as bad as you would think. So, you know, for example, in Bitcoin, there's like a fee-based system. So there's this issue of like I can send you outputs, right? And basically, if I send you, let's say I'm sending a transaction to you that spends 100 coins, and I only, you know, I use an input that only so I have an input to this transaction that's 110 coins, and then I send the transaction to you for 100 coins, which is what I was supposed to do, right? So then it turns out that that difference can basically be a fee that goes to the person who makes the block. So then you're further incentivized. But you are, if I'm reading you right, yes, there are many problems that come into this around like censorship, where like, you know, if someone doesn't want us to have a transaction, then like they could kind of put pressure on the people who are making these blocks, and then we just wouldn't be able to transact. But that's kind of, at least in Bitcoin, that's just how it works.
So a block may have any arbitrary transactions in it.
So how do the transactions flow to a node that's
Okay, so a bit that I haven't mentioned at all, so good question, but I'm also probably not going to talk about it here just for brevity, but basically every node on this network is participating in like a gossip protocol, which basically is just like peer-to-peer protocol. So the gossip word is like pretty informative. It's literally like, if I get a transaction, then like I'm connected to like some subset of you, and I just tell all of you about the transaction. And then in turn, all of you are connected to some different subset of everyone else, and they tell everyone. And then it again kind of spreads like we're gossiping some secret, or like not even a secret, but just some data. And then it sort of gets to the network. And then it just so happens that some of those nodes are miners, the ones making the blocks. You hope.
Miners are the ones making the block.
Yeah. So they're called miners. There's a whole bit on that we're getting to. There's many pieces to this. So yeah, you just kind of have to bear with all the pieces, and then hopefully it'll like kind of all make sense. Great, so here we are. So we basically can make this immutable log of histories of transactions. We again have this like strong sense of ownership that we love. So there's a problem though, which is that we kind of still at the block level lie essentially. We could have this problem where it's like, okay, I could basically sort of partition the network somehow, and then half the people could think one thing and half the people could think something else. And that was the double spin sort of problem I was trying to paint earlier, where it's like if I pull it off successfully, I could convince this Ferrari dealer that they should give me, you know, the coin, or they should give me the car for the coins, and then for the same coins, convince this Ferrari dealer that they should give me the car, right? So we generally don't want that to happen because like it's at that point, a currency is like kind of useless. So what are we going to do this? Or how are we going to do this? In general, this thing I was just describing is called a fork. And yeah, maybe I'll just skip this and get to the image. That hopefully explains a little better. But basically, what happens is you have conflicting blocks. Sort of two or more blocks are claiming the same parent, and so now you have to pick. Remember, you independently are making this decision, and the point is that you have to make it the same way everyone else is, but you might not be able to coordinate with them, and so that's why this is tricky. So here's more cartoons of this exact thing. So we have, this is supposed to be a blockchain, you know, happy blockchain, trundling along, adding blocks, more blocks, and then, you know, we're doing this thing, and oh, we see that there's now two blocks that point to the same parent, right? So now if we're trying to figure out, like, you know, which way should we go, we actually have to pick one of these. And so it's not clear how to do that.
How did they both arise?
So these miners, two different miners just independently made different blocks. And so, you know, they kind of raced to publish them to the network, and I eventually hear about both.
Okay.
I just don't know which one to go with. And then, I don't know, yeah.
One
Anyway.
of them has to win.
They will, you hope. So, you might not be able to see this, but basically, there's like different colored dots that are supposed to indicate different transactions. So again, this is where it's like, I'm spending 100 coins to this blue person, I'm spending 100 coins to this red person. And if I'm the same spending 100 coins, then like that's very much a double spend, like an attack on the network, right? Because if they both go through in some sense, then like I've gotten something for nothing.
But there could be a situation like this where they don't represent fraud or double spending.
So yeah, they could be legitimate. This could still happen even in a legitimate case.
Someone believes that it's making a valid block.
Exactly, and that happens. It happens pretty frequently. Forks happen. It's just you hope they're small forks and that they're resolved. And I'll explain how they're resolved. We do it by having this thing called a fork choice rule. So this is sort of baked into the protocol. If we don't all agree on our fork choice rule, then like we have no hopes at coming to consensus. That's why sort of, this code is, what we would say is consensus critical. It's like super important to get right. If you don't get it right, then like there's no hope, basically. And again, the point here is that you need an unambiguous way to figure out which arm of the fork you should go down when your decision is a function of everyone else as well, right? So even when you can't talk to them in like a synchronous manner, right? I don't have time to go and be like, hey, what is everyone doing? And then make my decision. I have to sort of independently, without talking to any of you, figure out which is the right choice. The way we're going to do this is we're going to, again, have our fork choice rule, and it comes down to this notion of work. Very much in the sense of like, I've put in some scarce resource into this thing, and so that's, the idea is that if I put more work into something, into one fork over the other, then that's the one that you should pick. So the way that we communicate this to other people on this decentralized network is via something called a proof of work. And a proof of work is just basically some data that's easy to verify, but it's very hard to generate, right? So again, sort of this like one-way function. So an example here, and this is what Bitcoin uses, is calculating the prefix of the hash, where the claim is like, okay, I need, you need to give me a block that has a hash, and the hash has to start with like some number of zeros. And the number can float and adjust, and that's fine. But the idea is that, if I need to give you one of these hashes with like 1 0, I basically, so there was the nonce field I pointed out earlier, I can just change that nonce and just cycle through nonces sort of brute force style until I find one that works. When I've done this, we say you've mined the block, I publish it out to the entire network, and the chain is extended. And it's great for me because I get a bunch of coins and everyone's happy. So yeah, again, it's this universal signal. I don't have to sort of talk to you or a third party or anyone to figure out if the proof of work is valid or not. I can check that independently. I again run the hash, which is comparatively simple with the data you claim, and then I can figure out if it's a good proof of work or not.
What if they're equal?
What if what's equal?
The difficulties, the work.
Right, sure. So you basically have tiebreakers. So you start with basically, yeah, you break. So the idea is that now instead of the blockchain, right, if you have a fork, there's now a block tree. And what you do is say for each node, there's a total difficulty of subtrees. And from there, you pick the highest difficulty. So that's the fork choice rule that I'm getting to. And if there's a tie there, you would then go to like, okay, well, like what's the earlier block? So every block has a time. So you could just pick the earliest one. Eventually, and this is sort of an eventual process, but eventually, as long as sort of hashing power stays constant, one fork will outrun the other, and then everyone will sort of jump over to that one.
Are you saying that some might have chosen the other block?
No, they will, because you don't know. So it's actually, there's this phrase people toss around like hash power's law or something. Basically, you vote with your hash power, and again, the hashing here is this like scarce resource, this hardware you're throwing at the problem, and you actually get to pick which fork you think is the actual chain. And the idea is then, if enough people agree with you, if the majority of the network agrees with you, then you're good, because everyone else has made the same decision.
How long could this take?
To do what? To resolve a fork?
Yeah.
They generally resolve pretty quickly, just because, so for instance, in Bitcoin, the block time is like 10 minutes. So the way that this works is that this difficulty number can float, and that basically implies how hard or easy it is to find these hashes. So if there's too many people trying at once, basically the block is found really quickly, so then the next block programmatically takes more work. Yeah, so in general, it's like, so many people are trying to do this right now that it's like a crazy amount of hash power, and it's like, like maybe 1 or 2 block forks happen, but then they generally resolve like after that, right? It's not that, it's like very rare that you have these like huge forks that are going forever, just because probabilistically, like, it just wouldn't make sense.
On the order of tens of minutes.
Sure, yeah.
This is good.
Well, so this is a complaint of Bitcoin, right? Is that like,
Transactions.
yeah, transactions could take forever, and like really, because of this, like maybe the fork could revert, maybe it couldn't. I actually need to wait some number of blocks. Basically, like if there's a transaction that has been mined, so it's on the chain in one of these blocks, I should actually, to be safe, I should wait more blocks, right? I should have more blocks be on top of that, because then I have more and more confidence that like the transaction's not going to revert. Exactly, yeah. So the general rule of thumb is you should actually wait 6 blocks, so that's like an hour. So like imagine if I'm trying to like buy a coffee from you and I have to wait an hour, you have to wait an hour. Doesn't seem to work. People are very much aware of this, and they're working on different blockchains handle this differently. So like in Ethereum, for instance, the block time is much shorter. It's more like 2 minutes or 20 seconds actually. Why? For this reason, you want a higher transaction throughput, just so more people use the thing and get utility out of it. And if I have to wait an hour to like kind of.
I'm not asking the motivation. I'm asking the mechanism.
It's like how not mine.
How? Yeah.
Right. So the 10 minutes is self-imposed in Bitcoin. It's part of the protocol to wait 10 minutes, basically.
Yeah.
In Ethereum, they just say, okay, wait like 20 seconds. And there are some like sort of subtleties to this in terms of forks happen more frequently if the block time is shorter, right? Just because the network can't synchronize as quickly. And then in Ethereum, exactly, or at least they do this thing where they basically incentivize, they basically pay you out for forks. It's called uncles or Omer blocks. But basically the bottom line is there's a way that they kind of make it work, and it's worked so far. So it's all this stuff. Actually, this is the disclaimer I probably should have given at the very beginning. All this stuff is like super experimental, and like you shouldn't really probably put any of your money in it if that's what you're trying to do. No one knows what any of this stuff is, and we're still trying to figure it out. So it's super fun, but it's super early days. Okay, let's get back on target. We have the fork choice rule here, and again, I'm just trying to like diagram this out, so I'll trace this. Basically, these blocks are labeled with their difficulty here, and we see that it was like 1 difficulty, and then 2, and then 4, and then 3. So we get to this fork, and then we choose this one, right? Because this is higher difficulty. Here we have a similar scenario where 1 block down, this was difficulty 10, so we should go there. This one is only 6, but then we get a final block that has 10, so now 16 is greater than 10, so we follow that fork. And we basically do this for all time, and that's how we resolve these conflicts.
And the people are picking the difficulty?
No. So again, the difficulty is programmatic. I will show you.
Yeah.
Okay. Let's see. Basically, it's based on the previous difficulty, and the way you change it is to keep this block time at 2 minutes. If that makes sense. So like, if the difficulty, if the difficulty is harder, then it will take longer, and then you can change the difficulty each block time so that on average you have 10 minutes in between blocks. Let's see.
Difficulty ever gone down on in the Bitcoin blockchain? Is the difficulty ever
It has, in the early days. not recently. Yeah. So I've kind of covered a lot of this in the questions that we just had. Basically, you have miners who make coins, and the reason they're doing this is they get paid coins. And sort of what users get out of this is that now the miners are the ones actually making everything work. So there's this nice symbiotic relationship. And there's this nice, sort of difficulty adjustment algorithm so that it says, basically we have a way to pick which fork to go down when we see a fork. If you'd like to, actually, okay. So I'll wrap up. Why is Clojure great? 2 things I want to point out would be just the interactivity to it. I don't know if another language that basically has the sort of same, that I can just sit here in my editor and try out code as I'm going, right? If I can type. But basically, this is great. It's right there. It encourages this sort of incremental development style. Stuart Holloway has this saying aim small, miss small, which I think makes a lot of sense here. sort of conceptually, you have immutability everywhere, which is great. It basically, if you're programming and basically if you're programming in an immutable context and you haven't sort of programmed in like an immutable programming environment, you should check it out because there's like so many things you don't have to worry about when this is the default. It's great for building protocol software because basically the idea is you can imagine this like functional loop of like I have an event that's going to have some effect on the state, which is going to yield more effects, maybe like writing to the network or something like that. So nice things there. Clojure has a great concurrency story. So like its atom type, I have a bunch of atoms over the code base because they're really useful for this kind of thing. Multi-methods are great just to call out some like smaller language features, and also that I can use question mark and variable names. I really like that. I don't know about anyone else, but it like really is great for me. Yeah, so any questions? I'll be around if you want to come talk to me. Please do. I love talking about this stuff. So yeah, that's that.
So are you trying to make the like a canonical Clojure implementation of the blockchain, or is this more like an experiment?
So there wouldn't be like a canonical implementation. So like for basically there's like different, so like, you know, Bitcoin's a blockchain, Ethereum's a blockchain, there's blockchains all over the place. And there are Clojure implementations to varying degrees. One downside to Clojure is that it seems like sort of as a community, you like, you know, you write maybe 80% of the library and then you like don't finish out the 20%. But basically, you know, to my knowledge, it's basically that situation for like, you know, like I'm sure we could find a Bitcoin, you know, Clojure implementation that like probably does most of the protocol, but probably not all of it.
Well, I was asking if that there is
Right. Well, yeah. I mean, this is not production ready. There's a few bugs left, but I mean, this is a blockchain. I actually want to put up sort of a live network. So if you would be interested in playing with it, there's my email. Just send me an email and I'll let you know. But yeah, you could basically put on a code, boot a node, and hopefully you would connect, and we'd all have the same state of the chain. This is called Stokes. It's my last name's Stokes, and there's tokens. So. Stokes. Okay, well then I'll hand it over to Derek, unless there's anything else.